so hello to everyone. I'm really happy to see you, even though I can't see you at the moment. But my name is Konstantin. I'm gonna tell you a little bit about our organization, about what we do, the software that we've built, and what you can do with this software. Just to get this out of the way, there's a couple of facts about the organization. So we started in November 2013 with a white paper written by a guy called Etherium. So we're almost 2 years old now. Ethereum is a non-profit organization that was crowdfunded back in August 2014. So we raised $18 million, and all of that money was raised in Bitcoin. So not a single penny went through bank accounts. Another nice thing, it was completely legal. Right now there's 43 of us. There's 3 major hubs. There's one in London, the communications team, which I'm part of. There's one in Berlin, which is the C++ team. There's one in Amsterdam, which is the Go team. And also there's some smaller hubs and people just traveling around the world. And probably the most important fact is that we launched just a couple of days ago. The article by the title of the article by TechCrunch probably describes it better than anything else. Vapor no more. But let's start from the beginning. I want to talk about the difference between client server and peer-to-peer. I mean, for many, these notions are quite familiar. So the client server, and this diagram is quite self-explanatory. The client server model, there's a server that computers connect to, and a peer-to-peer model, computers connect one to another directly. Probably another way to explain this is compare the difference between App Store and BitTorrent. So on one hand side, I've got a store with inordinate amount of power over apps, and on the other, you got a file sharing utility that, as it turns out, is pretty hard to shut down. So regarding advantages and disadvantages, well, the peer-to-peer model is nice in that it's got no single point of failure. You can dissect the network as much as you want, but it's kind of hard to kill. There's no intermediaries, which is also nice because there's nobody, if you need to send some sensitive data across the network, for example, I mean, there's nobody to sort of intercept the data or do some crazy stuff with it, like selling to third parties for ad revenue and stuff. And it's kind of, in that sense, it's sort of authority-free. The problems with peer-to-peer are that they're generally kind of hard to design and build, but most importantly, they're pretty hard to secure. So why is that? I mean, why can't we have peer-to-peer systems that are both they're nice in that there's no authority on the network, but they're also easy to design, build, and secure? Well, as it turns out, consensus at scale is a notoriously hard problem to solve. And some of you may actually recognize what these illustrations are illustrating. It's a problem commonly known as Byzantine generals problem. And it's a pretty hard problem to solve. I mean, there are solutions to it, but almost none are elegant, and definitely none are simple. However, enter the blockchain. It's generally a solution to the Byzantine generals problem. Maybe not a simple one, but definitely quite an elegant one. But without delving too much into generals and complex cryptography stuff, I find it's the easiest way to explain a blockchain to a developer is to describe it as a database. right? So stores data, right? You can read and write data into it and read from it. It's got some access permissions regarding who can write what stuff into the database and who can read what. And as it happens, it's got a massive redundancy set. However, unlike the database, it's got any updates to this database are non-reputable, which means that once you have written something, you cannot rewrite history. You cannot go back and, and like you would do with Git commits, you cannot cherry pick stuff. Now, once it's there for good, right? And another one is that it's got no servers, right? So every node in the network that makes part of the network essentially is a server and a client at the same time. All that stuff is powered by pretty sophisticated consensus algorithms. There's different implementations of different versions of them. There's proof of work and different types of proof of work. There's proof of stake, practical Byzantine fault tolerance, and so on. I mean, largely this is outside the scope of this presentation because you can talk about this stuff for hours. So I'm gonna skip this, but just keep in mind it's there. And as a result of that, we get a network that is very secure, it's practically undosable, and it's very interoperable. So interoperable in the sense that everybody who uses the network speaks the same protocol, knows how to interact with other nodes. Yeah, and there's another nice property, which is, and again, it's a network that is rather hard to kill. So the stuff that I talked about so far, I mean, it applies to pretty much any major non-cryptocurrency, right? Bitcoin, Litecoin, Dogecoin, and 160 others, 260 other coins. So how is Ethereum different? Well, for one thing, it's not a currency. Right, we are using the blockchain, but we're using it for data and logic. Right, the Ethereum blockchain has got an additional layer that allows defining custom business logic to organize the data, which is something that most other cryptocurrencies, if not all other cryptocurrencies, actually don't possess. And the key word here is custom. Yeah, we'll get to this in a moment. Even more importantly, this software allows you to build stuff on top of the blockchain easily, right? What you can do with it is build apps which are, once again, not subject to DDoS attacks. I find this is a really nice property, that are censorship proof. And generally, when you are dealing with a P2P network, it's kind of hard to block, as we proved with torrents. It's infeasible to compromise. Compromise in terms of data security and data integrity. Once again, because of the property of the blockchain, where once something is written into it, it's kind of impossible to take out. It's hard to maliciously modify any data stored on the blockchain. And it doesn't really need an infrastructure to go on, like no AWS. But how does this actually work under the hood? Yeah, so what you're looking at is called a smart contract. It looks a little bit like C++. It's a bit of a mix of C++ and JavaScript. More importantly, it's a high-level language. It's a language called Solidity. It's something we built internally, and this is what you would generally use to define your custom logic to organize data on the blockchain. So once you created something like this, you can deploy it onto the network, and if your code is correct and compiles, then it will be generally accepted by the network. It will sort of gain place on the network with something that lives on the blockchain. Yeah, contracts, once deployed, can be referenced by addresses, just like any account in Bitcoin. It has a static reference, which the address never changes. Once created, it can never be modified, which sort of gives you a guarantee of consistency over execution. It can interact with other contracts and other accounts. It generally works as a push mechanism, so contracts cannot make calls themselves unless you call into them. Yeah. And and they are programmed in high-level languages. One of them is Solidity, another one is called Serpent, which is a bit like Python. You can write all this stuff in a text file, save, use some client tools to deploy it, but it's better to use an IDE. And here's one that we built internally at Ethereum. It's called Mix. And this allows you to debug your contract. It allows you to test them, deploy onto the network. And if you don't happen to like this one, okay, well, there's a web-based community-built one. It's called Cosmo, and allows you to do pretty much the same thing, maybe it's something different, but it works in browser. There's JavaScript API, which you generally use to interact with the contract. So JavaScript, as many of you know, is something that actually runs locally. Yeah. So once you deploy the contract, you can make calls into it. Here I'm using the same contract I showed you previously. Now that it's deployed, I want to send some coins out. I should have mentioned the contract that I showed you was basically an implementation of Bitcoin in 9 lines of code. So here we are interacting with the contract. We declare a bunch of addresses, then we call sendCoin, which is going to send a transaction onto the network. The transaction basically tells the network to call function sendCoin of contract MetaCoin and pass it the value of 10. And if I've got enough balance to send 10 coins to Bob, then I can later do a console log in it, call check balances for Bob's address and convert it to string, and I'll get 10. And the interesting point here, the important point here, is that anybody who runs this JavaScript on their machine, or the last part, the console log, will also see the same number. So we're kind of in consensus. Once I send the transaction, the new state of the system is observed by every single node in the system. So if you want to interact with the network directly, we've got get, which is our command line client. This is something that we massively stress tested over a very long period of time. We've been bombarding it with transactions for almost 3 months. It went through 2 security audits. So generally I would consider it pretty secure software. However, if this low-level stuff is not your cup of tea, well, I mean, you can use Embark. If you just want to build stuff, yeah, and if you just happen to be into Node.js or Meteor, of course you can use Embark, which is another community-built framework that generally just simplifies a lot of that stuff. So you can create, debug, test, deploy, redeploy contracts. You can easily wrap them in the JavaScript code that just makes it very convenient to interact with them. So I already mentioned there's a Meteor plugin for it, as well as Node.js. And there's even an IPFS integration. IPFS is decentralized file storage. So if you wanted to distribute, your app on the network, share it with friends or others, you could do that without using a centralized server. If you do happen to be into low-level stuff, okay, well, we've got 4 official implementations for you to play with. There's a Go client, which is just Geth that I just showed you. That's the this is our front runner. There's a C++ client, which is the high-performance implementation. There's Etherium, which is mainly for educational purposes, as well as building your own custom implementations of the protocol and building private blockchains. And Ethereum GSLib is more of a collection of different utilities rather than a client, although it can work as a client. But If you want to play like super low level networking stuff, then and basically this is your best choice library. There's more. We also got our decentralized file storage solution, which is called Swarm, and Whisper, which is a P2P encrypted messaging protocol. Well, all of these tools, when used in conjunction, can allow you to build applications which are much like traditional Web 2.0 applications, 1.0 even, but they don't require centralized, don't require any centralized servers or the users having to trust anyone with their data. The users can just interact directly, and on the outside, the UI will look just like any web app. So, has anyone actually built anything with it? Well, absolutely. There's been quite a lot of use cases and quite a lot of different interesting implementations. So on the Internet of Things, we got IBM on their Adapt project, where they built a washing machine that could automatically order detergent once it runs out of it. There's Airlock, which are building smart locks for hotels, where you can send a payment to the system and will match your private key with the private key of the lock and unlock it for you for a certain period of time. It's prediction markets, Augur, which is one fantastic implementation of decentralized trust protocols. There's use cases in finance, so Digix Global is a company that allows you to create gold-backed digital assets. So if you want to buy an ounce of gold and you want to move it from Singapore to London, you don't have to physically move it. You can register in one place and you can claim it in the other. Maker is an implementation of e-dollar as well as decentralized bonds. E-dollar is a particularly interesting thing. So those of you who have been following Bitcoin might be aware of crazy fluctuations in price. So Bitcoin has been very volatile. But e-dollar is cryptocurrency that is pegged to the value of $1. Which is some pretty complex contract difference mechanisms to power it. There's decentralized crowdfunding app, which is called Wayfund. Allows you to run crowdfunding campaigns once again without Kickstarter or anybody else taking commission on your on it raised crowdfunding. In reality, I mean, these are just a couple of use cases, and there's way more. If you want to find out more, check out dapps.ethercast.com. There's about 76 different projects on this website, but I know for sure there's way more of them. And the reason is, like, when somebody asks me, like, okay, so what can you actually build with this? I usually get a little bit puzzled, because it's the same as to ask somebody, well, what can you build with C++? Anything, really. I think the better question is, what do you want to build? And I think that generally concludes my my presentation, or at least the slide part of my presentation. I want to say thanks to the sponsors, and that's that really. I'm happy to answer any questions.
Thanks, Konstantin. Any questions? Just hang on a sec. I don't know how far this thing goes.
Goes far.
So the smart contracts, they're a part of the blockchain. How are they secured, and how does a client or a peer know whether they've been tampered with?
How does are they secured, and how does the peer know whether they've been tampered with? Is that a question?
Yeah, if the smart contracts are part of the blockchain.
Yeah. So that works much the same way as Bitcoin transactions are secured. So on the blockchain, a series of events are recorded in transactions, which are in turn recorded in blocks, which are then added to the blockchain. Once the block is added to the blockchain, the block itself presents cryptographic proof that it's the correct, it's the valid block that has the right to be there, and it's kind of hard to replace it. I would recommend to look into the proof of work system to get the explanation of why it's hard to rewrite history on the blockchain. But generally, because of the way this mechanism works, blocks that have been created a long time ago usually have much higher security than the new blocks. So once you write something, once you create a smart contract and write it onto the blockchain, the longer you wait, the less likelihood that somebody can change something about this contract. And another thing is that addresses on the blockchain are unique. So say, let's run a scenario where I want to create a contract where I would transfer you the ownership of a house upon your transfer of, well, say a certain amount of money to the contract. And then somebody else wants to take my contract, replace it with another one where they get forwarded ownership of the house as well as the money. And they can they do it? And the answer is no. And the reason is that every time you create a contract, it actually is identified by an address which is absolutely unique. So if somebody else was to create a contract, they could, but they would not be able to reuse the same address. And the address of the contract is how you reference it. Okay? So if they wanted to create this sort of malicious bad contract, that it would be a completely separate entity, would be completely different, and it would have a different address. Yeah. So, and I'm talking about the case where they would somehow be able to fork the blockchain, throw massive computational resources, fork the blockchain, and just create a different series of events. While forks are possible, it's not do absolute damage. I mean, you can cause certain damage with forks, but it's still sort of limited. Does that answer your question?
Yeah, thanks. You're talking about a 50% attack.
Yeah. Yeah. So 50% attack can create a fork, right? So yeah. So I was referencing 51% attack.
All right, thank you.
All right.
Any other questions? Another great one.
One quick question. I think it's at some point during your slideshow you referenced working on private blockchains, and your platform would support that. With that, how would you sort of roll that out on a large scale to sort of overcome that 50% attack? Say I wanted to create an international property selling company or consortium. How would I actually sort of distribute it through like CDNs, or how would I actually get that mass to make it stable enough to actually roll out a private blockchain from the get-go?
Actually, great question. So there's two different types of private chains. So one type is a private chain that you would just generally create locally for testing, and it's a trivial case because you're not too worried about security when you're testing. The more interesting kind of private chains are so-called permission ledgers. And permission ledgers are generally private, that type of private chains is something that organizations like financial institutions are looking at the moment. And generally there are different ways to secure such protocols. Generally speaking, it doesn't make sense to use proof of work. So one thing you could do is create a set of nodes and run a proof of stake algorithm. And because you are a centralized organization, it becomes a little bit easier to secure the blockchain because you can allow only certain nodes to create blocks. So you can control which nodes on the network are allowed to mine or create new blocks. Now, it can get a little bit more complex if or problematic if one of these nodes get compromised, but then you are mostly worried about the majority of the network being compromised rather than small parts of it. And yeah, so if you wanted to roll out a private chain within an organization, it's probably best to use the Python client because it's quite easy to swap out a proof of work for something else. As I mentioned, there's proof of stake, or you could use practical Byzantine fault tolerance. But yeah, so bottom line is it's a little bit easier to secure private blockchains when they are semi-centralized.
Okay.
Because of centralization purposes.
Cool. Thanks.
All right.
Anyone else? That's it?
Just one question. How have you found that the legal community has been responding to this technology in Europe?
Well, I'm probably not the best person to ask about that, but from what I've heard, I'm not sure about Europe, but in the UK so far, the general feel about cryptocurrency is quite positive. The commissions generally just want to find out what this is and how they can regulate. And a lot of this stuff is very new to them. Like, for example, how do you go about crowdfunding campaigns? What is a crowdfunding campaign on the crypto space? Is that an IPO? Well, probably not really. Is that a private funding? Well, not really. So yeah, I think that they're having a lot of some problems sort of pigeonholing this at the moment, or finding relevant laws or changing the system. But again, from what I've heard, there's not been like a massive negative attitude to it here in the UK. The situation may be a bit different in other countries.
Thanks.
Thanks, Konstantin.
All right. Thank you.
Thank you very much.